Hello everyone. In today's video, we're going to be taking a look at three definite integrals involving absolute values. I often find that students get intimidated when they are faced with problems involving absolute values. So the goal of today's video is actually to build some confidence and see how we can solve problems like this. You will see that there is one major trick or one major theme in how we can actually tackle most of these problems. So let's get started. Just before we begin with the first problem, let's review the definition of the absolute value function. The absolute value function takes as input any real number, and what it outputs is the number x if that number is non-negative. So if you give me an input that happens to be positive or 0, then I will just return the same input. Whereas if the input you give me happens to be a negative number, then I will multiply with a negative sign to make it positive. So the output is always going to be non-negative of this function. And the main thing to take away from here is this case analysis that we do based on the sign. If the number happens to be non-negative, we just output that number as is. Whereas if it happens to be negative, then we just attach a negative sign to make it positive. So this case split based on the sign is really the important part. And what we'll see is that instead of absolute value of x, you could have absolute value of, x minus 7 or 2x plus 3 inside absolute values. And what that will do is just shift where the cases get split. And that is really the key idea, understanding where is the definition changing. If you can define these pieces, you will be able to integrate no problem. Okay, so having a look at example 1, we are asked to find the value of the integral from 0 to 1 of the absolute value of 1 minus 2x. And the first step will be to understand where does the sign of 1 minus 2x change. And to do that, we can just solve 1 minus 2x equals 0, and this will give us x equals a half. And now what you can do is just reason what happens to the left of 1/2 and what happens to the right of 1/2. Or you could also do it a little bit more formally by solving a couple of inequalities like I've done here. So we can check when is 1 minus 2x bigger than or equal to 0. And then solving this inequality gives us that we must be to the left of 1/2. Another way to see this, if you just want to reason in your head, is just pick a number to the left of 1/2. So for example, you can pick 0. Well, when I plug in 0 here, you can see we just get 1, right? And 1 is bigger than or equal to 0. So doing this analysis allows us to write the absolute value of 1 minus 2x as a piecewise definition. So the absolute value of 1 minus 2x is just going to be 1 minus 2x as long as the input x is to the left of 1/2. And otherwise, we will have to attach a minus sign to the output if x happens to be bigger than 1/2, in which case 1 minus 2 is negative, so that's why we multiply by the negative sign. Okay, so now we can actually tackle the integral. So we'll begin by drawing a small diagram of the number line. So I'll mark 0 and 1, which is the interval over which we're integrating, and then 1/2 lies in the middle. This is the point where the absolute value of 1 minus 2x changes sign, right? Depending on if we're on the left or right of this, we will have to use a different piece. And just before we actually solve this integral, as an aside, I want you to consider the following two problems where we just change the interval over where we're integrating. So instead of going from 0 to 1, suppose I was trying to find the value of the integral from 87 to 100. Well, on this interval, we're way to the right of 1/2, right? And so on this interval, we're always going to take the bottom piece. So I can replace the absolute value of 1 minus 2x with just minus 1 minus 2x, right? And then you can, this is just a polynomial, you can integrate using the power rule and solve no problem. Similarly, let's say instead I was integrating from minus pi to 0. Well, in this case, all my x values are to the left of 1/2, right? And if we're always to the left of 1/2, then the absolute value of 1 minus 2x is just itself because it's going to be positive. So therefore, we can just simply replace the absolute value of 1 minus 2x with just 1 minus 2x. And this is just a simple polynomial which we can integrate no problem using the power rule. Now, where it gets a little bit tricky is if we're trying to integrate and the the point where the sign changes happens to be in that interval, which is what the case is here with our original problem. We're integrating from 0 to 1, and at 1/2 the sign changes. So the idea here would be to, instead of integrating from 0 to 1 in one shot, we'll split it up into two cases. We'll see what happens. So we'll do the integral from 0 to 1/2, and then we'll add on the integral from 1/2 to 1. And on each of these two separate subintervals, we can solve no problem just by using the definition of the absolute value. So with that approach in mind, we can write the integral from 0 to 1 of the absolute value of 1 minus 2x. We split this at the splitting point 1/2. So we have the integral from 0 to 1/2 plus the integral from 1/2 to 1. So this is one of the properties of the integral. You can split at a point. And now on this first integral, we are always to the left of 1/2, right? So if we're to the left of 1/2, then the definition of absolute value of 1 minus 2x is telling us we can just drop the absolute values because it's always positive. And on the other integral, we're always to the right. When we're integrating from 1/2 to 1, we're always to the right of 1/2. And the definition tells us, well, we can just drop the absolute values, but we have to multiply by a negative sign. So I did that here, and that gives us 2x minus 1. I also multiplied by the minus. You can change the order of the terms. And now these are just two polynomials which we can integrate. We have two definite integrals with some polynomials which we can integrate no problem. And I carried out the work here. You can check it out. The main idea was really understanding this case analysis. But the answer we'll get is 1/2. Okay, now let's get started with the second problem. The second problem is the integral from -1 to 1, and then we have a nested absolute value. So we have an absolute value, and inside that absolute value we have two absolute values. I know it looks complicated, but it's going to require the same ideas we looked at in the previous problem, except that we have to do a little bit of more careful case analysis. So we'll begin by once again identifying what terms have absolute values, right? In this case, there are really two main terms, the absolute value of 1 minus 2x and the absolute value of 1 plus 3x. We'll identify where do these terms change signs. And the way to do that is by solving where does 1 minus 2x equal 0? Well, that happens when x is equal to 1/2. And now you can just reason, like we did above, what happens to the left and what happens to the right of 1/2. And this will let us write the definition, the piecewise definition of the absolute value of 1 minus 2x. So you'll see that whenever you pick a number to the left of 1/2, then the absolute value of 1 minus 2x is going to be non-negative. So we can just drop the absolute values. Whereas if you pick a number to the right of 1/2, then you will have to multiply by -1 because the 1 minus 2x will be negative. And to do this, you can just pick a test point. Like for example, you can pick 0 in the first case and you can pick 1 in the second case. Or if you want to be a little bit more formal, you can always do the inequalities like we did above. Set up the inequalities and solve. Just make sure that if you're going with the inequality approach, that you flip the sign if you are multiplying or dividing by a negative number. Similarly, we do the same thing for 1 plus 3x, right? When does this equal 0? Well, it will equal 0 exactly when x is equal to -1/3. This allows us to write the piecewise definition of the absolute value of 1 plus 3x. And once again, we just have to check what happens to the left and right of this point. So, for example, if I pick any number larger than -1/3, for example 0, I could plug 0 here, you'll see that the output will be non-negative. So in that case, I can just drop the absolute values. And if I pick a number that is to the left of -1/3, then you'll see that actually, let's pick for example -1. I pick -1, then I plug that in here, I get 1 minus 3, which is negative, right? And again, you can prove this a little bit more formally by just solving some basic inequalities, or just reason through it like this. In any case, you will have to multiply by a negative sign if you want to drop the absolute values. Okay, so now we can actually make a diagram. Well, we're integrating from -1 to 1, and there's these two special points at -1/3 and +1/2. At these points, uh, there's terms in my integrand that change sign, right? So what we'll do now is, instead of integrating from -1 to 1 in one shot, we'll actually split it. We'll integrate on -1 to -1/3. We'll also integrate on -1/3 to 1/2, and we'll integrate on 1/2 to 1. And then we'll just sum the results up. So here's what we get, right? We have the integral from -1 to 1 of this guy, and this is going to be equal to the integral from -1 to -1/3 plus the integral from -1/3 to 1/2 plus the integral from 1/2 to 1. The integrand stays the same, and now we'll solve each one of these separately. Okay, let's start by solving the first piece, which is over the interval from -1, which is over the interval from -1 to -1/3. Well, in this case, we are to the left of a half. Since we're to the left of a half, we're in the first case over here. So that means we can just drop the absolute values on the 1 minus 2x, and for absolute value of 1 plus 3x, we are once again to the left of -1/3, right? So this time we actually have to pick a negative sign. So if we want to drop the absolute values on 1 plus 3x, we have to multiply by a minus sign. So that's what I've done here. We have the integral from -1 to -1/3. So don't forget the outside absolute values, but inside you can see the absolute value of 1 minus 2x is just itself, whereas the absolute value of 1 plus 3x, I can drop the absolute values, you just have to multiply by a minus sign. We simplify this and we get the absolute value of x plus 2. And now we just have another basic absolute value integral, right? You can do the same steps. You can find where does x plus 2 equal 0. Well, it happens when x is exactly equal to -2. Then you want to see, okay, well, what happens before and after this point? And you'll see that right now we are actually to the right of this point, right? On this interval from -1 to -1/3, we are actually to the right of -2. And what happens when we're to the right of -2? Well, we are going to be positive, right? Like pick any number bigger than -2, like for example -1, and you'll get a positive result. So that means I can simply drop the absolute value, right? As long as x is on the interval from -1 to -1/3, the term x plus 2 is always going to be non-negative. So we just drop the absolute values. We have a simple polynomial which we can integrate using the power rule, and you'll get 8/9. Similarly, we can now solve the second part. So this time we're integrating over the interval from -1/3 to a half. So let's see, we are to the left of a half, right? We're to the left of a half, and we're to the right of -1/3. Well, let's see what happens to each of these cases if we look at our definition. So since we are to the left of a half, I can just drop the absolute values on 1 minus 2x. And since we are to the right of -1/3, that means we can also just drop the absolute values on the 1 plus 3x, because both of these terms are going to be, the insides are going to be positive. So that's what I've done here. We have the integral from -1/3 to a half, and you can see we can just drop the absolute values on 1 minus 2x, and we can drop the absolute values on the 1 plus 3x. Just make sure you put brackets around it because the minus sign has to distribute. And don't forget the absolute value on the outside. We simplify this and we get the absolute value of -5x. Now what we can do is just get rid of the minus sign, and we can pull the constant out, and we just have to solve. We're left with the following integral. It's 5 times the integral from -1/3 to a half of the absolute value of x dx. And now we can solve this integral. It's another absolute value integral, and we have to consider cases. Again, what happens, when does the absolute value change sign? Well, in this case it's pretty obvious, right? It happens exactly at 0, right? So that's where we're going to make the split. We're going to see what happens to the left and what happens to the right. Well, on the interval from -1/3 to 0, we are negative, right? So I have to integrate minus x dx. And on the interval from 0 to 1/2, I have x is positive, so I can just drop the absolute values. So you can see now we're getting more comfortable with this. We don't have to write out the full cases and consider when when is things positive, things negative. You can sort of understand what's going on. The idea is just to split cases at where it changes sign. In this case, it's pretty obvious. It's just the regular absolute value function. The sign changes exactly at 0. So you want to consider what happens to the left of 0 and what happens to the right of 0. Okay, well, once we have done that, we just have to do two definite integrals of just polynomials, right? Just a linear term. And you can do the work and you'll get 65 over 72. Okay, great. Now let's do the last piece, which is going to be the integral over the interval from 1/2 to 1. So again, we are to the right of 1/2. That's what I want you to take away here, is that we're to the right of 1/2, right? So if we scroll up to see our definition, what happens when we're to the right of 1/2? Well, the absolute value of 1 minus 2x picks up. If we want to drop the absolute value here, we have to actually pick up a minus sign. And similarly, for the absolute value of 1 plus 3x, we are to the right of negative 1/3, right? So in this case, 1 plus 3x is already positive, so you can simply drop the absolute values. So that's what I've done here. I have dropped the absolute values and picked up a minus sign. And for 1 plus 3x, I've just simply dropped the absolute values, and make sure you put brackets so that the negative distributes. Don't forget the absolute values on the outside. Once you simplify, you get another instance of an absolute value problem. And now you can do a little bit of simplification here if you want, basically by factoring a minus sign and then using the property of absolute values, that the absolute value of a product is the product of absolute values. This negative sign can just go away. And so really we're integrating from 1/2 to 1 the absolute value of x plus 2. And again, now you might be getting used to this. We just have to see where does x plus 2 change sign, right? And you can do that just by checking when does x plus 2 equal 0. Well, it happens at minus 2. And then you want to see what happens to the left and right of minus 2. So in this case, we are to the right of minus 2, right? We are integrating over the interval from 1/2 to 1. So for example, if I was to plug in like 1 here, right, I will get something positive. So as long as you're to the right of minus 2, this quantity will be positive. So that means we can just drop the absolute values. And now we're just integrating a basic polynomial, a linear function here in this case. And you can apply the power rule and get 11 over 8. Finally, we can solve our problem. So if you recall, the goal was to integrate this integrand from -1 to 1. And we broke it up into 3 pieces. And now we have actually solved all 3 pieces. So the answer to the original problem is just the sum of our 3 answers, the sum of these 3 integrals. And that happens to be 19 over 6. And finally, let's take a look at our last problem, which is the integral from -2 to 3. And we're integrating the absolute value of x squared minus 2x minus 3. So in this case, there's not really any linear terms yet. We're integrating the absolute value for a quadratic function, a second degree polynomial. So the idea here will be to basically factor this polynomial and get it in terms of linear factors. So factoring x squared minus 2x minus 3, using whatever method you wish, using for example the quadratic formula, you will see that this factors nicely into x minus 3 and x plus 1. And this tells us that the roots are x equals 3 and x equals minus 1. So making a diagram, we're integrating on the interval from -2 to 3, and our points of interest happen to be at -1 and 3. And the reason why these are important is because on these subintervals, like for example from -2 to -1, these factors will take on different signs. And as a result, their product will influence what the sign of the original quadratic is, right? And to see that a little bit more clearly, the absolute value of x squared minus 2x minus 3 is equal to the absolute value of the following product, right? So what we're going to do is we're going to split the interval from -2 to to 3 into two subintervals. We're going to consider what happens on -2 to -1 and what happens on -1 to 3. So on the first subinterval, from -2 to -1, the x minus 3 factor is going to be negative, right? As long as x is less than 3, this will be negative. Similarly, the x plus 1 factor is also less than or equal to 0. This will happen as long as x is less than or equal to -1, which we are on this interval. Okay, so then x minus 3 and x plus 1 both have to be negative. So that means their product, the product of two negatives, makes a non-negative. And also, what is this product? It's exactly our original quadratic, x squared minus 2x minus 3, right? So that tells us that, well, if this quadratic is non-negative on this interval, then I can just drop the absolute values, right? So the absolute values can simply be dropped and I get this. Similarly, let's do an analysis on the other interval from -1 to 3. Well, once again, we are less than 3. Since we're less than 3, x minus 3 will be negative. And x plus 1 will be positive in this case because we are bigger than -1, right? This will be positive as long as we're bigger than -1. So when I take the product of these two factors, I have a negative and a positive. So their product will be negative. And so therefore, the absolute value of the quadratic in this case, if I want to drop the absolute values, I have to multiply by a negative sign. So we are trying to evaluate the definite integral from -2 to 3 of the absolute value of x squared minus 2x minus 3. Well, based on our analysis above, we are going to split it into two integrals. We're going to go from -2 to -1 and then from -1 to 3. And based on our analysis above, we know on the first interval, the quadratic happens to be completely positive, right? So we can just drop the absolute values. And on the second interval, we know that our quadratic happens to be negative. So in order to drop the absolute values, we pick up a negative sign. And now we're just integrating two polynomials, which we can do using the power rule. And I've done the work here. You can pause and have a look, but your final answer will be 13. Okay, so now that we have solved the following three problems, I hope you are a little bit more confident in tackling problems that involve absolute values, and you will see that they're not too bad. Some of them can be a little bit of work depending on how many absolute values are involved, but you just have to do a little bit of careful analysis on when the sign changes. The goal is basically you want to get rid of the absolute values, because once you do that, you'll just be integrating a regular polynomial, and those you're probably very comfortable with. If you found this video helpful, you can let me know by leaving a like button or a comment down below. You can subscribe for more math videos in the future, and if you have any questions, please feel free to leave them in the comment section below.